Hey guys, today I'm going to talk to you about Apache Hadoop. But before we talk about Hadoop, I think it's important to cover the precursors to Hadoop to understand more about the atmosphere at the time. I think the most influential development for Hadoop was the Google file system. The concept was first introduced in a white paper in 2003 written by Sanjay Ghemawat, Howard Giboff, and Sung-Tak Wang. 2003 was a pretty crazy time for Google and data in general. Google needed to create a file system that was reliable and scalable without sacrificing performance and cost. This came at a time where the internet was booming and people were really beginning to see very large data sets. There were four really important observations that were made about the current systems that led up to the conception of the Google file system. The first was that the component failures should be treated as norms and not the exception. They suggested in the paper that the quantity and quality of components guaranteed failure in large databases, so they aimed to develop a file system that could accommodate for these errors easily. The second feature was that files were getting larger. It was normal to get files that were multiple gigabytes and even sometimes data sets that were in the multiple terabyte range. The third observation is that most files are mutated by appending rather than a direct overwrite. This includes data like streams and also a lot of data analysis methods. Take Twitter, for example. You're not going to be making overwrites. You're just going to be kind of analyzing the data and maybe appending occasionally. Google basically said that a lot of the new data coming in doesn't require write capability within the file. The fourth observation is that co-designing applications with the file system's API benefits the system. This is kind of common sense to me. I mean, if you design a file system with a use case in mind, then obviously the file system will benefit. So what did they come up with? Google developed a distributed file system capable of processing large data sets that successfully accommodated hardware failure by using a lot of inexpensive commodity components instead of a few expensive units. The use of inexpensive commodity components also enabled linear scalability. Increasing the database size was as simple as adding more inexpensive units. This image is an example of a given cluster on the Google file system. A cluster is comprised of a single master node and multiple slave nodes called chunk servers. Both the master and the chunk server can be accessed by multiple users, and the users actually have to talk with both the master and the chunk server in order to process data. Now I'm going to give you a brief breakdown of what elements make up a Google file system cluster. I'm going to start with the chunk servers. Chunk servers house the actual data sets. So first the data sets are broken down into 64 kilobyte blocks, and we call these chunks. It doesn't really have to be 64 kilobyte. That's kind of what they are broken down by default, but you can change that if you want. After this, they're kind of distributed across the chunk servers. So the chunks are replicated 3 times, and then they're put on different chunk servers. And this way, it kind of protects against individual chunk server failure, and that's what I was referencing earlier. So the master node, which is outlined in this blue box, that houses all the metadata. So the namespace, the access control info, the file to chunk mapping, but it does not keep a persistent record of the chunk location and replicas. It stays up to date through the use of something called a heartbeat to monitor each chunk server. The heartbeat is like a ping. It kind of pings each chunk server, and it kind of lets the master know that the chunk server is still online, and it also provides useful information kind of for chunk management and load balancing. So let's say there's one server that kind of has too many chunks on it, and it's starting to get kind of bottlenecked, then it'll redistribute different chunks to other servers. Finally, the client must communicate with both the master and the chunk servers, like I mentioned earlier, in order to read and write. that is. The client gets the chunk locations from the master and then communicates with that specific chunk server directly. So it asks the master, where's this data? And then it will go directly to those chunk servers. And all of the actual computation is done on those chunk servers. So that was a brief overview of how the Google file system worked. And you'll see later how Hadoop, how influenced Hadoop was from the Google file system or by the Google file system. Now I'm going to talk about the probably the second most influential paper that Hadoop bases a lot of its framework off of, and that's Google's MapReduce paper. So in 2004, Google published a paper that outlined an easy way for processing large data sets called MapReduce. And if you're not familiar with it, it's a programming model that allows for parallel computing using kind of assumes a cluster-based data structure. The general outline is two functions. The first function is the mapper, and the second function is the reducer. The mapper takes key value pairs and outputs a list of key value pairs. So it reads in key and assigns key value pairs, and then it outputs a list of, I guess, the file it wrote of those key value pairs. And then the reducer takes a key with a list of values, then outputs a list of values defined by the key. If this is kind of confusing you, I'm going to explain it in a lot more detail later on in the lecture, so just hold on to that knowledge and we'll come back to it. So the takeaway from MapReduce is it's an extremely efficient way to process structured and semi-structured data. It's fault tolerant, so it'll re-execute things when nodes or things have failed. There's automatic parallelizing and distribution, and I/O scheduling to efficiently use the network, and you can monitor the entire process. Like there's a monitoring function or feature where you can see like the entire job running. The next paper I'm going to talk to you about is the Google Bigtable paper. So the Google Bigtable paper was published in 2006, and it basically outlines this database called Bigtable that is a scalable NoSQL database that sits on top of the Google file system. And remember how I mentioned the Google file system was developed to manage, multiple or data sets ranging from multiple gigabytes to terabytes? Well, Bigtable was designed for petabytes of data. And the way I look at this is, at the time, Google was was coming up with a bunch of applications like Google Earth, Google Maps, and even the Google search engine. And that required a ton of data storage and kind of processable data storage. And so they came up with Bigtable. And of course, since it is built on top of the Google file system, you still use MapReduce for read and write, and it's still comprised of a bunch of low-cost commodity hardware. So right here, in this figure, I have kind of like a really basic example of how Google Bigtable works. Essentially, the client will communicate with the clustering scheduling master, which will communicate with the scheduler slave to start the job. So that'll start the job. And then the chunk servers talk to the Google file system master. And then the Bigtable master coordinates servers and is responsible for load balancing. And then the Bigtable server serves the data. Now I'm going to talk briefly about the Bigtable data model. You can think of it as a distributed multidirectional sparse map. The way I think about it is kind of like a big table. There are unique row keys, which is normally an arbitrary string, and then there are columns, kind of like a table. At the intersection, there are these cells, and these cells can hold timestamps and potential edits. So in this figure, let's say I wanted to edit the HTML. So what would happen is it wouldn't be a direct overwrite. It would be more like an append to the data set. and the append would come with a timestamp of the edit. This allows you to store multiple versions of the same content in those cells. The big table data structure also supports transactions within a single row. Rows in the big table data model are ordered lexicographically, and that means that numerical and alphabetical, I think. Rows close together tend to be on the same machine. Larger tables in the big table data model are split into tablets. Tablets are 100 megabytes to 200 megabytes in size. And each machine has about 100 tablets on it at a given time. So you might be wondering, why are the file sizes so small, and why does each machine have so many? So think about kind of like recovery times. It's much easier to distribute smaller file sizes across more servers than it is to distribute a couple of large files. It also allows for easier load balancing. So that's pretty much all I'm going to talk to you about the big table data model and kind of big table in general. But I think it'll come back up, or the structure will come back up later in the lecture. So this brings us to Hadoop. Now I'm going to go over a quick brief history of kind of how Hadoop came to be what it is. In 2002, two men named Doug Cutting and Mike Caffarella were attempting to build an alternative search engine called Nutch. When Google released the Google file system in the MapReduce papers, Cutting and Caffarella saw this as an opportunity to improve the indexing capabilities of Nutch. They began to try and implement a similar system as the one described in these two papers. Neither paper provided physical code other than small examples of queries. The Google file system was coded in C++. The system Cutting and Caffarella were developing was written in Java. In 2006, Cutting was acquired by Yahoo, whom at the time wanted to create an open source platform that resembled the Google file system with MapReduce functionality. The project was called Hadoop, after Cutting's son's yellow stepped elephant toy. The project was eventually handed over to Apache. So that's kind of like a really brief overview of what happened. For the most part, they saw these papers and they were like, hey, we should just make an open source platform that can do the exact same thing, because Google really outlined some very significant methods for processing large data that hadn't really been, published before. A lot of people kind of said that they were using things that were similar, but, a lot of people say things. So there are four main components to Hadoop: Hadoop Commons, the Hadoop file system, MapReduce, and Yarn. Hadoop Commons is just the core utilities and the libraries required to run Hadoop. This includes the physical files that are necessary to start the platform. Hadoop Commons also contains the abstractions required for the file system. Hadoop Commons is the core of the Apache Hadoop framework. So HDFS, or Hadoop file system. The Hadoop file system closely resembles the Google file system in that it is a distributed file system that uses a master-slave relationship to communicate. The Hadoop file system consists of a name node and data nodes. The name node is essentially Google file system's master node for the Hadoop file system. The name node contains permissions, modifications, versions, and access times. The name node also holds a map used to locate blocks in the data nodes. In the Hadoop file system, the default name node file is split into block sizes of 128 megabytes. Data nodes are essentially the same as the chunk servers in the Google file system. The blocks are replicated by default 3 times across various data nodes. The default data node size is 64 megabytes. And this diagram right here is pretty much what happens during a write request. So the client talks to the name node provides 3 spaces for the potential data nodes, because it has to be added in triplicate, and then the client writes the data to the data nodes. Now I'm going to go over kind of the Hadoop file structures. I guess you could say it's sort of version control. So there's a couple concepts you need to understand before you really get a good handle on how the Hadoop file system works. And the first is the image. Image is the inode data and the list of the blocks belonging to each file. And that's stored in the image. And the image is stored in the RAM of the name node. A journal is incremental changes. And these are logged on the local file system of the data nodes. Originally, there was a secondary name node, and the secondary name node reduced the amount of data built up on the primary name node by creating checkpoints. A checkpoint is created by taking the original image and adding the journal, creating a new image. In the current system, instead of a secondary name node, there is a checkpoint node and a backup node, or a backup node. They work very similarly to the way the secondary name node worked. The checkpoint node creates a checkpoint using the journal and the image, and then re-uploads the checkpoint onto the name node. The backup node is an optional feature of the checkpoint node. The backup node creates a checkpoint, but it also stores a copy of the checkpoint locally before transferring it to the name node. This is just, just in case the name node fails or there's some kind of weird transfer error. I mean, it makes sense to use the backup node for the most part. So now I want to explain why the MapReduce framework is such a big development for large data sets. Here we have a traditional way of managing large volumes of input data. In this example, we have a large set of car names and we want to get a counter of the number of times that each car is mentioned. Normally, we would divide the data into smaller sets, then grep, and then compile matches. Or we could divide the larger data sets into smaller data sets and then write a loop to iterate through the data and count, then compile the counts. Both methods would take a large amount of time. This is how the MapReduce method would process this file. The mapper is responsible for splitting the data into key value pairs and then compiling those key value pairs into lists. As an example is shown below in the diagram. In this example, the data is cars, like I mentioned before. The data is first split into manageable amounts, then assigned key value pairs. The pairs are then combined into lists that represent each data subsection. The output is then piped to the reducer. The reducer takes these lists of key value pairs and makes a list of values given a key. These lists are then compiled to output a list of key value pairs for the entire dataset. This is shown in the diagram below. Matching list entries from all lists are grouped into new lists. These lists are then consolidated. The final output is a list with a total of each key. In this example, the output is a key type of car, and the value is the number of times in which the car appears in the dataset. The fourth process, or kind of component of the Hadoop framework, is YARN. YARN stands for Yet Another Resource Nanny. Originally, Hadoop did not include YARN. Hadoop was primarily used for simple MapReduce functions. YARN allows for simultaneous processing of multiple different types of applications in a Hadoop cluster. YARN works by tracking all the resources in a cluster. This is done by adding one extra machine to the cluster. This machine houses the YARN resource manager. Every application within the cluster also requires an extra node, which serves as the application manager. The application manager communicates with YARN, giving YARN complete knowledge of the available resources. This allows YARN to manage resources for each application and balance and accommodate load accordingly. This diagram kind of shows what's going on. The application manager communicates with the resource manager, the name node still communicates with the data node, and the client communicates with the resource manager and the name node, which is all contained in the master. So HBase is a column-oriented data management system that runs on top of the Hadoop file system. It's almost the exact same thing as the Bigtable file system that I talked about earlier. It groups data by column families so that the same column entries would be housed on the same server. This transforms the data stored into Hadoop into a NoSQL database or NoSQL database. It has pretty simple commands like get, put, scan. And then there's a pretty simple query language, and then you can combine it with a more complex data language like Phoenix, which creates a SQL-like layer on top of HBase. Now I want to talk about other things that you can build on Hadoop. The first is Pig. It's a very common package that people often build on Hadoop. It allows you to write complex MapReduce codes using a scripting language called Pig Latin, and then Pig translates the Pig Latin into MapReduce so that it can be executed with Yarn. Hive is also really common. Hive provides a SQL-like interface to the data stored on the Hadoop platform. It's a data warehousing infrastructure, so you can essentially write SQL-like queries on Hadoop data. Impala is built on top of HBase. It's an open source, massively parallel processing SQL engine. And Swoop, you can basically transfer relational database or relational data to Hadoop, and I think vice versa. So Mahout's a cool machine learning library. It does really common math operations and some machine learning algorithms. It's really nice for data scientists. Uzi's workflow management. Zookeepers does some cool stuff with kind of like system checks and like backing up data. It's often used for rolling upgrades and hardware shutdowns. Flume, it's kind of like a streaming feature. I guess it's not exactly streaming, but it injects data as it's being generated and puts it into a cluster, and that can be really cool for a lot of things. So my initial project, I was supposed to compare and contrast a relational database and Hadoop, and the more I learned about it, I mean, the more I realized it's kind of comparing apples and oranges. If I had to say, I mean, the MapReduce framework, map can kind of be thought of as like a group by, and then the aggregate function, and then the reduce can kind of be like an aggregate function in SQL. Hadoop definitely scales better than I think a relational database would. It can also process unstructured or semi-structured data, like just random text or like Twitter feeds and stuff like that. Hadoop by itself doesn't have a schema, so it's not really structured at all. I mean, there's some kind of semi-related, and there's not even, no, it's not structured at all unless you build things on top of it. So, I mean, it'd be really weird to compare and contrast them. So, do you guys have any questions?